Yeah, the wave function. Wait, so I have a question. Can you explain something to me? What's the Hamiltonian operator?
We haven't done that yet.
Oh, okay.
Yeah, we just started this class.
Well, if you find out, let me know.
I will.
Because you know the pivot one?
Yeah.
I didn't read it fully. I thought it was pivoting this one. I thought it was pivoting this one instead of this one. And so I got the first one wrong like 10 times, and then I did yes or no. Yeah. Oh, we dropped a piece of this.
Wait.
I still got it.
So for the pivot thing, it was just like, it just goes flat. It doesn't like go like this.
Yeah, there's one bar like this, one bar like this, and it goes like that.
Oh, that makes so much sense.
I thought it was going like this. I don't know why.
You know what? I made the same mistake. Don't worry about it. It's okay.
Okay, good morning everyone. Let's get started. Okay, a couple of quick things. For the most part, and I would imagine particularly up until midterms or finals are coming up, possibly you don't have much reason to look at notes that I post on coursework. But one thing that I've realized, as we mentioned, is there are not infrequently some additional work problems in my notes after each class. So take a look at those and maybe some additional materials to just get a bit of practice with. Doesn't seem to be much use of Piazza. And I realized, having looked at it this morning, I'm not exactly sure how my responses get posted there. Because I usually respond when something comes into my email just by replying, and it seems to get posted in Piazza in a way that's slightly not what I expected. But anyway, bottom line is I want to encourage you to use it. It's a good way to just get community discussion going and hopefully sort of problems associated with homeworks, etc. It might be a kind of nice way to get input from your peers quickly. And then a reminder, again, doesn't seem to have been used much. I sort of prompted maybe over the weekend, I can't quite remember. For those of you who are interested in finding study partners, to use that discussion section on Courseworks. Again, not too much traffic there, but if you're still interested in finding people to work with, and you know how much I recommend and endorse that, then please just use that section to try and find people to study with. And then the lunches that I talked about maybe last Thursday, hopefully you saw confirmations of those up on Courseworks maybe yesterday. Those 4 lunches were filled, so I guess a quick question. Any of you who didn't get to sign up still interested? If so, raise your hand. Okay, modest interest. Okay, we'll see if I can schedule one more. Okay, good. So, I'm going to talk today initially about the concept of center of mass. We've already introduced it a little bit, and all being well, that'll go relatively quickly, and we'll be able to transition into the topic that's going to occupy us for at least the next 3-ish sessions, I would estimate, which is to do with rotational motion. So, quick heads up of what we're covering. Center of mass, briefly touch on the idea of center of gravity, which is very much related. And then we'll start introducing rotations, we'll introduce variables, conventions, and very quickly start using the tools that we developed in the first couple of weeks of semester and carry them over to apply them to rotations as opposed to translational motion, okay? So kinematics. What I want to emphasize right up front and throughout is much of that is by analogy. So pretty much the same processes we went through for linear motions, we will be going through but more rapidly for rotational motions. And again, I'll say it a number of times, if you're feeling a little bit confused as we start discussing rotational motions, it's not a bad idea always to step back and say, okay, what was the linear analog to this, and can I just relate it back to that, and hopefully that's going to get you back on track very quickly. So that works very well through most of rotational motion. It gets a little bit more complicated when we talk about dynamics, so forces in rotations. But again, a lot of this works by analogy. And if we have defined the appropriate quantities and variables for rotations, we'll see that the equations and the behaviors we've studied for linear motion very much carry over to rotational motion. So there's a nice sort of strengthening synthesis of ideas, but at the same time it's applied in a new context when things are spinning. So that's the roadmap for this morning. Okay, so let's come back and talk about center of mass. We have pretty much throughout, up until now in the course, we've idealized objects as being point-like, and now we're going to extend our considerations to where that's no longer relevant or appropriate. And we're going to look at objects that have real physical extent, so they have real size. And that's an essential kind of forerunner to the idea of rotations, because something's rotating more or less by implication it has some size, not necessarily truly, but more or less it has some size. All right, so what's the idea of center of mass? Roughly speaking, it's a position-weighted mass. Sounds slightly abstract. We'll define it formally in just a moment, and for those of you who've been working hard on this week's homework, which I imagine is most of you, you've already gotten some exposure to this. I purposely asked the recitation TAs to do one problem on center of mass calculation simply because we didn't get to it at the end of Tuesday's class. So I'm hoping you've already had exposure to it in recitation as well. So in words, how would I kind of describe this? It's the point, a special point on an extended object, which if we're looking at how that extended object behaves under the influence of some external force, we can simplify our considerations by effectively identifying this special point, the center of mass, and then stating, really, which is true by observation, that the object will move in such a way as though any external forces are acting solely at that point. So it's effectively a special point. We can imagine, for purposes of outside forces acting, that all of the mass is concentrated at that point. And so we can go back and in many respects treat it as point-like in that context. I mentioned on Tuesday some of the areas where this is going to be relevant, aside from rotations. And again, you've gotten some practice with this already, which is in the concept, for example, of momentum conservation, where if we can identify the so-called center of mass of some composite system, if there are no external forces acting on that system, we expect there to be no change in motion at the center of mass. So we can kind of identify in collisional contexts or explosional contexts this special point, the center of mass, and again, under the assumption no external forces, or no net external forces to be precise, are acting, we should have assumed that that center of mass motion continues sort of as it was with no change. So these are all ideas that build into the idea of center of mass. And before we define it, settings where it's important. So I already mentioned these, but I do just want to write them up. So it's in the sort of context of collisional, that's the word, explosive type events. If no net external force, we expect the motion of the center of mass to be unchanged. Okay? So, the example, a fair number of you have been scratching your heads over on this week's homework has to do with a nice example of this. This person who's walking along the length of a canoe while the canoe is essentially free to move, it's floating on the surface of water. How does this help? Well, we can think of the center of mass of that system, but first off, before we say anything about it, we better ask ourselves, are there any net external forces acting on that two-object system? So a person inside a canoe, well, there are certainly some external forces. There's gravity, presumably, and then what we might sort of count as a normal force. A little bit different in this case because the canoe is floating, so that's not a normal force in the sense that we've really discussed it so far. We'll replace it in a couple of weeks by the idea of a buoyant force. Most of you are familiar with that. But again, the idea is in terms of net external forces, there aren't net external forces acting on that two-object system, the two objects being the person and the canoe. And therefore, regardless of the sort of motions of the two objects, the person and the canoe, we should expect that the center of mass of that object remain stationary in this case, because it started off at some position. We should expect that it remains in the same place. And so with a little bit of head scratching and figuring out how you're going to define positions at the center of mass there, you should be able to solve that problem, recognizing that the center of mass does not move in that case. More generally, what about cases where we do have external forces acting? Again, this idea of center of mass can help simplify our considerations. It could be at any scale in physics that you might be interested in. Large-scale motions of things, like on the sort of cosmological or astrophysical scale. You might have complex systems, maybe solar systems or binary star systems, things like this. And if we can identify the special center of mass position of those systems, we can treat any external forces acting on them, gravity perhaps the most likely one in this scenario. We can imagine gravity acting solely at the center of mass of that system, and the sort of system moving in step in some respects when we consider that center of mass position. And then on the other end of the spectrum, it's often useful, maybe when we're talking about atomic or molecular systems, we want to figure out the influence of net external forces acting on them. Again, if we can identify this special point, the center of mass, then we can treat it as though all of those external forces are acting at that point. Okay, so a lot of kind of rambling words there, but I'm hoping you're getting a sense of the utility of using this idea and this concept. So let's go ahead and simply define it. It's a fairly straightforward definition, and I think this is the most concise sort of wording to describe it. We can define the center of mass, and I'll define it right off the bat in 3 dimensions. So let's just call this the 3-dimensional position, R, of the center of mass. So it's the X position of the center of mass in the I-hat direction, plus the Y position in the J-hat direction, plus the Z coordinate in the K-hat direction. Nothing very profound about this, it's just recognizing that in general we'll be dealing with objects that may be 3-dimensional. But we can also confine ourselves to 2-dimensional or 1-dimensional objects. And in each of these cases, we want to define what the individual coordinate center of masses are. And so a couple of things we can do here. We can do it for discrete assemblies of objects, or we can do it for a continuous distribution of mass in some objects. We can do it both ways. So here's the first one. I could, for example, write this as, let me write it as following. So I've got an assembly of discrete objects, which I'm just going to label A, B, C, D, so on and so forth. And let me just write this up, and then come back and talk about it. Okay, so this list could go on as long as we wanted to, but let's say I've got 3 objects, A, B, C, and D. So how are we defining in the X direction the position-weighted mass? Well, as the wording suggests, it's pretty straightforward. We're going to take each discrete mass, in this case the mass of object A, and weight it or multiply it by its position along the x direction in whatever coordinate system we've selected to make it helpful. So, position-weighted mass for each object, we're adding them together, as you would expect, summing them up, however many there are, and then we're simply dividing by the total sum of the masses. Okay? So, a pretty straightforward definition. In the case of an assembly of discrete objects, of course, this is just the total mass of the system. So this would be for discrete masses, discrete objects. We'll use that sum. More typical, I would suggest, is going to be the case where we have continuous distributions of mass. So I'm going to put and or here, and we'll talk about some problem-solving strategy in a few moments, but the other way I could write this is for continuous mass distribution. I'm basically going to write this in a much more concise way as 1 over the total mass of the system. Again, now times the position-weighted mass distribution. So if it's continuous, we're going to write it like this. For each small mass element, dm, presumably has some particular coordinate position, in this case in the x direction. We're going to weight it again, and we're simply going to do the integral to sum up the entire mass distribution. Okay? So this is going to be for a continuous mass distribution. So that's the definition, and of course we would have similar expressions in y and z if we're dealing with an object that has finite extent in y and z, respectively. Everyone okay with that idea and the formal definition of it? Yeah? Okay. Good. Some things we're going to be helped significantly by two considerations as we try and figure out the positions of center of masses. First off is, in the case of continuous mass distributions, the question of whether or not the density of that object is constant. Clearly, if it is, it's going to simplify our calculation. If it's not, then this integral becomes slightly more complicated, but in principle, all of you have the tools to be able to solve it. So the question of uniform density will be one important consideration. So let me maybe just write these two things down. So simplifications, quite often, one would be uniform density. And most of the problems we'll deal with will correspond to that case. And the second thing to think about is whether the objects have obvious geometrical symmetries, okay? Start doing some maybe quick practical examples of this. Meter stick. Sort of seems from your perspective maybe one-dimensional. Of course, in practice, it's three-dimensional. But let's say, looking at it from this perspective, let me tell you that this is a roughly uniform density meter stick. It's made of wood. Presumably the wood is approximately constant density. Just by looking at our definition of the position-weighted center of mass here, or here, if you like, for a continuous object, and if I tell you it has uniform density, just by virtue of symmetry of this object, of the shape, what would you predict to be the position of the center of mass of this object? The center of the ruler, right? The center of the stick. And of course it is. So this is actually demonstrating this from the point of view of how it behaves in response to a negative square force. So what forces are acting on this right now? Well, what forces are acting on it? I'm holding it like right now. What forces are acting on it? Yep.
Gravity and a normal force from your hand.
Yep. Debatable whether we call it a normal force. If I did that, I'd be happier calling it a normal force, but it doesn't really matter. Yes, so two forces acting on this thing right now. So gravity downwards and a normal force upwards. So this special point, the center of mass, In many respects, it'll allow us to treat this object as though net external forces are acting at that point. But life will get more complicated if we start to look at non-symmetrical or non-uniform density situations. So, it's a little bit of a cheat here, but now I'm going to do something which might, in some respects, be able to be treated as two objects. And this is where the idea of taking a system that's complicated and simplifying it stepwise will quickly become apparent. You've had some practice with this already on this week's homework. Let me just draw this schematically. It's not quite true, but let me draw it schematically as follows. So this is a simple example. Here's my uniform meter stick. And because I've told you it has constant density and it has clear geometrical symmetry, you've told me correctly that if I look at this in isolation, its center of mass is at the geometrical center. But now I'm simply going to take this and add what I'm going to assume. Well, maybe let's explore it a little bit more. It's a separate mass that I'm going to stick on the end. And let's be slightly realistic here. It's certainly probably not uniform, but it's certainly continuous. So it's some kind of clamp. So it has some real extent. But presumably, of course, this thing has its own center of mass. So what I can do in situations like this that have two or more objects is I can break this down stepwise and ask the question, well, maybe if I look at this object only, can I figure out where its center of mass is? Let's say for argument's sake, it's right there. And now I have a particular mass for my ruler. Let me just call this the mass of the ruler, and this is the mass of the clamp. And so what I can do now is when I'm figuring out the overall center of mass of this system, I can take those two separate objects. Having separately found their individual centers of mass, I can treat those as point-like objects at this point. So this is the center of mass of my clamp at this point. And now, in many respects, I'm free to treat this as simply two point-like masses and resort to this calculation to figure out where the center of mass is, okay? So this is a two-step process that you're often going to be doing. Again, you've had some practice with this already in this week's homework. We're taking two or more objects which are perhaps continuous. We're finding out their individual center of masses. Once we've identified them, we know the location, we know the masses. We can revert to our more simple calculation of finding the center of mass of discrete objects to get the answer. All right, so it's pretty obvious how this goes. So I simply add this to the end of here. What you expect qualitatively is true for where the center of mass of this two-object system is now. Say that again? Sure, closer to the clamp, right? So without this, of course, I've got my center of mass in the middle, but again, quickly applying this, either in actuality or conceptually, you'll recognize that the center of mass of this thing is moved towards the right-hand side, and I can find this empirically simply by finding the kind of balance point. And again, there's a little more behind this than I'm letting on right now, but there we go. So, all right. So, okay. A couple of other things. I'm trying to move through this quickly. Of course, it's entirely possible for the center of mass of some system not to be physically located within the system itself. And again, already seen examples of that in the homework. So classic examples of where objects have center of masses that are not within the actual extent of the object themselves, things like bagels, donuts that have holes in. If they are symmetric, not spherically symmetric, but rotationally symmetric, of course there's a hole in the middle. So the center of mass of your bagel is in empty space, but again, that's the point at which we can effectively consider any net external forces to act on that bagel if we're trying to analyze the bagel's motion. Okay, so I think rather than work through stuff which I'm expecting most of you have had decent experience with just in the past couple of days on the homework, I'm going to ask you, the couple of homework problems that have to do with center of mass, how many of you feel you sort of have questions about that still, or things they're unsure of? And be totally honest here. Okay, a few of you. All right. So let me then do a couple of things. Let me do an example. So we've got an object as follows. Three uniform rods in the following configuration. So somewhat comparable to things we've seen in the homework. This one has a mass 3m, this one has a mass m, this one has a mass m, and we are told that they are all of length L. Okay, so each of these is length L. And we're going to be asked to find the position of the center of mass. So let me write this as R center of mass. Okay, so these are uniform rods, and we want to find out the center of mass. Okay, so good example of what we were just talking about, of this sort of two-step process of taking things that are intrinsically continuous, but looking at symmetries and kind of breaking down the problem into a two-step process. So how would you be inclined to figure out the position of the center of mass on this setup first? So I didn't really talk much about problem-solving strategies. There's maybe not too much to say, other than it might be wise to pick a certain point on the object that will help us in the calculation of the position of the center of mass. So a sensible choice of a coordinate origin might help us. So how might we set up our coordinate system here, and then how might we figure out the actual center of mass in, let's say, an XY coordinate system? Any recommendations for how we'll do this? Yeah?
Put the origin.
A little louder?
Put the origin of the coordinate system in the volume of the mass.
That one? Okay. We certainly can. Doesn't matter where we choose. Given that there's apparently uniform density for each of these three rods, and looking at symmetry, might there be other choices that make our life slightly easier? Just go right to the back. Okay. Yep. Here. Let me just probe you a little bit more on that. Why would you choose that point?
Because your formula is mx, so you have a distance of 0 from your mass now once in the vertical.
Yep. Okay, so you're starting to explore some of the ideas underlying this, and again, it takes a little bit of practice to figure out what might be an easy choice of coordinate origin. But it turns out that yes, there is some advantage to choosing a point like this, perhaps, over a point like this. The reason being, what we're going to do is rely on uniform density and symmetry considerations for each of these three rods, look at them separately, figure out where their individual center of masses are, and then combine them together as though they are three discrete objects as opposed to three more complicated continuous objects. So recognizing that, obvious, I think, where the center of masses of these three rods are treated separately. So this one, since it's uniform, it has a mass 3m, has a length L, it's uniform by symmetry. Its center of mass is presumably here. And then for each of these two, again, by symmetry and knowing that they're uniform density, the center of masses of those are presumably at the geometrical centers of those, okay? So we can simplify our algebra if we in fact choose our origin at being one of these points. because then maybe the x and or y components of the position of the center of mass of that object fall out of the equation. Now again, it's going to work wherever you choose, so long as you do it correctly, but it may be that you have less work to do if you choose the coordinate system appropriately. All right, so let's maybe choose this one, and it's, I think, a nice place to go with. So in this coordinate system, where is the position of the center of mass? I'm just going to write this as x, y. So what are x, y for, let me label these things.